All right, y'all, we're going to do a quick video on section 2.4, polynomial and rational functions. The polynomial portion of the notes should be covered from the notes that we handed out at the end of last week. For the actual handout for the notes for the rational functions, I might give you all a blank whenever we get back to class next week. But for the problems, we'll just be working a few of them from the book to kind of properly discuss what we need to for this section, okay? First thing, we're going to read through the polynomial and rational functions. We're going to read through the polynomial definition. This says a polynomial function is a function that can be written of the following form right here. And it looks a little bit intimidating, but really the things that I like to lock in on right here is that you have something right here serving as your highest power thing, so x to the n, and then you start having cascading degrees of powers until you get to a constant term right here. So this could be x to the fourth, x to the fifth, whatever, but this is your largest term right here, and then you have a potential term for everything between that up to your constant term, with all the little a's out in front being the corresponding coefficients with those various powers of x. That's why we call n a non-negative integer, and we call whatever that highest power is, that non-negative integer, the degree of the polynomial. And like I said, the coefficients, the a's, are real numbers with that leading coefficient not equal to 0, because otherwise that whole term would cancel out and then we wouldn't really have that as a leading coefficient, right? The domain of any polynomial function is a set of all real numbers. So not quite like much quite like the quadratic functions, the domain is also all real numbers. We don't have any division by 0 issues or any negative square root issues, so that's fine. And these are some important properties that I've also listed on here, in addition to what the textbook says, just to kind of give you some ideas about what the general properties of these guys are. It says a positive leading coefficient, your a sub n, indicates the graph rises to the right. A negative leading coefficient indicates the graph falls to the right. A polynomial of degree n can have up to n x-intercepts, but it doesn't necessarily have to. And then finally, the graph of a polynomial of degree n will turn at most n minus 1 times. And this will be, this last one in particular will be helpful with a lot of the homework questions, because it asks you to determine what the minimum degree of the polynomial can be whenever you're looking at some pictures. And here, at the bottom of the notes right here, I do have a couple of examples to look at with that in mind. Here it says, for the following polynomial graphs, determine what is the minimum degree of the polynomial and whether the leading coefficient of the polynomial is positive or negative. Well, let's look at the minimum degree first. Maybe I'll write that. I bet I can scratch that below in the margin right here. We'll do minimum degree. And then we'll talk about the leading coefficient. I'm just going to abbreviate that LC. Now for the minimum degree, all we're going to do is we're going to go through and we're going to look at how many times the graph is turning. And here I see I have 1, 2, 3 possible turns right here, which means that the minimum degree of the graph has to be at least 4, since I see that it turns 3 times. And then whether or not the leading coefficient is positive or negative, well, just look at the end behavior on the right side. If it's negative, that means that our leading coefficient is negative. Conceptually, this just means that since that negative leading coefficient is going to be dominated by that leading term right here because it has the highest power, eventually it should be having that downward end behavior. We can do the same type of argument on this one for B. The minimum degree, we can just count the number of turns. Looks like we have 1, 2, 3, 4 turns. So that means that our degree of our polynomial is at least 5. And then for our leading coefficient right here, it also has to be negative because we're falling to the right. Again, it's a little bit different than the other one because we are rising as we go to the left, but specifically we're looking at the end behavior of the right side right there. Since it's falling, we're going to say that it has a negative leading coefficient. So that's all we're going to do to talk about polynomials for now, is how to look at identifying some of those important characteristics from those graphs. Now what we're going to go ahead and do is we're going to take a brief detour and we're going to talk about some rational functions. I'm going to go ahead and pull up our text real quick. I have the book right here with me, and I'm going to go ahead and flash the definition for a rational function, and then we'll talk about some examples with that. Okay, so rational function. This is a function that can be written of the form f of x is equal to nx over dx, where dx is not equal to 0, where n and d are just polynomials that we just talked about. The domain is a set of all real numbers such that that bottom function is not equal to 0, because otherwise we'd have that division by 0, right? So we got to be a little bit careful of that. Let's go through an example of these rational functions real quick. We'll do example 1. In the function I'm going to give us to play around with first is f of x is equal to 3x over x squared minus 4. And we're going to ask some questions about this guy and play around with them. The first one that we're going to look at is to find the domain. So to find the domain of this polynomial, or sorry, this rational function right here, really we just need to look at what parts of the denominator are going to make this be 0, right? If we figure out x values that make the denominator 0, then those are the values that we want to avoid, right? Kind of like we saw for our domain issues earlier. So what we do for this is we set x squared minus 4 is equal to 0 and then solve for it, right? If we look at this, we see that we'll have x squared is equal to 4. We can take the square root of both sides and we get x is equal to plus or minus the square root of 4. And then that means that x has got to be equal to either negative 2 or positive 2, right? Now, notice that this is not our domain answer right here. These are just the values that we have to avoid for our domain. So whenever we make the claim for what the domain is, we're going to really say that it's all numbers except this positive and negative 2 right here. And I probably shouldn't have written it so far off. I'll go ahead and write it below right here. But whenever I'm actually listing out the domain, I want to say all numbers but negative 2 and positive 2. So I'll do negative infinity to 2, negative 2, union negative 2 to 2, and then union 2 to infinity. So hopping over those 2 points right there and creating these 3 intervals, this would be the domain of this particular rational function, okay? Let's look at B next. B is asking us to find any x or y intercepts, so we'll look at how we find x and y intercepts for this rational function. Let's focus on the x-intercepts first. I said before, whenever we were looking at the quadratics, that we could find x-intercepts always by setting the function equal to 0. So f of x is equal to 0. In this case, f of x is 3x over x squared minus 4, which means that we just need to find where this function, what values of x are going to make it equal to 0. Right? Well, easiest way to do this is really just to isolate the numerator piece, right? If you wanted to, you can think about multiplying both sides of this equation by x squared minus 4. That would make the left-hand side cancel out, and then 0 times x squared minus 4 would just be 0. So really, all that you need to do is look at the equation 3x is equal to 0, right? Well, that can be solved just by saying x has got to be equal to 0. So that means that this guy right here will serve as our x-intercept then. For our y-intercept, all we have to do is evaluate f of 0. Well, whenever we evaluate f of 0, we'd have 3 times 0 over 0 squared minus 4. That would just be 0 over negative 4, or 0. So our x and our y-intercept, we have one. They're both the same point and they're the origin point. So we have an x-intercept at 0 and a y-intercept at 0. So y is equal to 0 for our y-intercept, x is equal to 0 for our x-intercept, right? Let's do a quick reminder on how to figure out the vertical asymptotes. Now, we've actually already done the work for this. To find the vertical asymptotes, you're just going to figure out what values are going to make your denominator 0. So for example, what I'm going to do is I'm going to isolate the denominator piece. I'm going to call it d of x, I believe is what we called it in that previous definition. F of x is equal to, I think we called it numerator function and denominator function, so n of x over d of x. And what we're going to do to solve for vertical asymptotes is we're going to solve for this denominator piece. Solve dx is equal to 0 for vertical asymptotes. Okay, so since we're looking at solving these guys for vertical asymptotes, what we can do is we can say, d of x is equal to x squared minus 4. That's what we said was the denominator piece, and we just need to set this equal to 0. So we'll do x squared minus 4 is equal to 0. And whenever we solve this, like we did for the domain, we will basically do the same thing. So add 4 to both sides, take the square root, and we saw that x has got to be equal to either negative 2 or positive 2 whenever we ended up solving that out, right? So really here we have two different vertical asymptotes then. We have, I'm going to write it maybe below to the left right here. Sorry, I'm a little bit all over the place. Vertical asymptotes. We have one at x is equal to -2, and we have one at x is equal to +2. Okay. So those are our two vertical asymptotes that we have for this problem. And that would be the answer to part C right there. Let's go ahead and look at part D next. Part D is asking us to find horizontal asymptotes. And as a reminder, the function that we had is f of x is equal to 3x over x squared minus 4. Now, in a moment, I'm going to give you the rules for finding the horizontal asymptotes. There's really three different cases that we have to be aware of. The first case is if you're in like a bottom-heavy case where the degree of your denominator, the degree of the denominator is higher than the degree of the numerator, and in this case we are. In this case, it's going to lead to a horizontal asymptote of y is equal to 0. So we can say y is equal to 0 is our horizontal asymptote because the x's degree is bigger than nx's. So the degree of the denominator is bigger than the degree of the numerator. And again, I'm going to do a quick flash of the rules after this problem to kind of remind us of all of these rules, but put a pin in that for just a moment. So our horizontal asymptote would be at y is equal to 0. Finally, what we're going to do is we're going to look at graphing this with all the information. Graph f of x is equal to 3x over x squared minus 4. Okay, and we're going to kind of combine all of the information that we have up to this point so far in order to help us do this. All right. So first, what I'm going to do is I'm going to go through and I'm going to just draw in any asymptotes that I have, and maybe I'll do it in maybe a green color. The first one that we have is at y is equal to 0, and that's going to be a horizontal line that is cutting through the point y is equal to 0, which means that we're just going to have a line across the x-axis right here. Now, because it's right on top of the x-axis, I'm just going to do it a little bit above it to tell myself that it is there. And then we also said that we had vertical asymptotes at x is equal to +2 and -2. So I'm going to add those vertical asymptotes in there as well. So here's my vertical asymptote at x is equal to -2. And here's my vertical asymptote at x is equal to +2. Okay? Now that we have this, we can go ahead and start to look at what our function might look like. We have a few important points that we do know. We know that 0, 0 is a point on our graph for certain because this is our x-intercept and our y-intercept that we calculated back in that first step, which means that we know that it's going to have to cross through this at some point. And now, typically what we do as a general rule is we come up with a list of points that are between each asymptote and point that we know exists so that we have a better idea of what's going on with the graph. Because the asymptotes are going to show us where the lines are going to follow on the graph, but we don't know which quadrant of the graph each of these pieces is going to be in. So basically what we need here is a collection of maybe 5 different test points so that we can know, or maybe 4, 1, 2, 3, 4 different test points so that we know where the graph is lying in each of these locations. So what we're going to do first is we're going to actually do some test points over here in a table. I'm going to call them x and f of x. And we're going to strategically choose them to be outside the asymptotes and in between the x-intercepts. So let's maybe do the following ones right here. Maybe I'll do -4. That would be a good one. I'll do -1.7. I'll do +1.7 and then +4, right? The reason why I've chosen these right here is because they fall between these important intervals. -4 is outside of this asymptote. -1.7 is in between this asymptote and this origin point right here. You can choose to do -1 exactly. That might have even been a little easier, but I've already run the calculations for these. 1.7 again between these two right here. And then we also have +4 out here. Whenever we run these calculations through f of x, we get -1, -5.3, negative 4.6, and then positive 1. Those are the values that we get for all these guys, right? Oops, sorry, I made a slight mistake here. This negative 1.7 is supposed to be positive 4.6. I repeated that measurement there for some reason. Let me make sure that I've got this right one more time. Negative 4, negative 1, negative 1.7, 4.6, positive 1.7, negative 4.6, and then 4.1. Now we've got everything correct. Let's go ahead and add these additional points that I've put onto the graph right here. So I'm going to add a tick mark up and down. And it looks like we need to go all the way up to 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 1, 2 to go up to 4. 1, 2 to go out to 4. All right. So adding my point at negative 4, negative 1 would get me down here. Adding my point at negative 1.7, positive 4.6 would get me about right here. Again, it doesn't have to be perfect, but as long as it's in the approximate location. And then adding it at 1.7, excuse me, 1.7 negative 4.6 would be down here. And then 4.1 would be up here, right? Now what this tells me then is I need to approach the vertical asymptotes from the given directions that I have these points being mapped out in. Here on the left-hand side, I'm going to have to hit this point, and I'm going to go down toward this vertical asymptote in this direction, and then hug the horizontal asymptote in that direction as I've done there. For this next part, between these two vertical asymptotes, it looks like I'm going to be hugging this vertical asymptote on the upper side and then hugging this one on the bottom side, but I also have to cross through the origin. So I'll have something like this. Oop, that was bad. I probably should have started a little bit more over. Something like this. There we go. Okay. Again, we get really, really close to the vertical asymptotes, but we don't actually cross through them. You can't cross through vertical asymptotes. And then finally, this one is going to hit the vertical asymptote from the top, or hug it at the top, and then it's going to follow the horizontal asymptote as we go off to the right. That's why we needed these points that we added, these 4 points, because if this point would have been up here instead in the top left quadrant, then we would have had to graph it in this quadrant instead. Same thing with this piece right here and this piece right here. It all depends on whether or not they're above the y-axis to determine which vertical asymptote they're going to hold. But this, in total right here, what we've graphed, is a good representation of a good sketch for this function right here, okay? Wonderful. Let's really quick, before I forget, flash those rules for the horizontal asymptotes. Again, this is directly from the text. Here is the vertical and horizontal asymptotes of rational functions right here. It says to consider the rational function f of x is equal to n over x, n of x over d of x, where the n of x and d of x are polynomials. This describes how to get the vertical asymptotes. We'll talk about what happens whenever they do have real zeros in common, whenever we canceling and such. This previous case that we did not have any canceling, so you could just set the denominator equal to 0 and solve for it. But if they did have any cancellation, we would have taken care of that first. For a horizontal asymptote, there are 3 cases. Like I said, if the degree of the numerator is less than the degree of the denominator, like the previous case, then y is equal to 0 is a horizontal asymptote. If the degree of the numerator and denominator are equal, then you take the, excuse me, the ratio of their leading coefficients. So a is the leading coefficient of n of x, and b is the leading coefficient of d of x. In case 3, if the numerator is greater than the degree of the denominator, there is no horizontal asymptote. There may be what is called a slant asymptote, but I don't think we're going to worry about it at any point during this course. If we do need to worry about slant asymptotes, I'll upload something else about that, or we'll have a discussion about it in class. Okay. Wonderful. Let's go ahead and look over one more problem with this asymptotic behavior business. I'm going to slide this over, and we're going to look at this. Example 3. There we go. What we're going to look at now is f of x is equal to 3x squared plus 3x minus 6 all over 2x squared minus 2. Okay. First thing that you should do, oh, we have the instructions for this. Sorry, I forget we're not working for notes. What we're looking for here are to find vertical and horizontal asymptotes. Okay. So what we want to do here first is, because these things aren't completely factored, is we want to work through this, and we want to factor as much as we can from the numerator and the denominator. So I'm going to work a few steps of algebra right here, focusing on the numerator and denominator as separate pieces, and I'm going to start factoring what I seek in factor. In the numerator, I noticed that a 3 can be pulled from all these terms that we have right here. So we'll have x squared plus x minus 2 after we pull a 3 out. And in the denominator, I realized that we can pull a 2 out, so we have 2 times x squared minus 1, right? It looks like these guys even factor a little bit further. You can use your AC method / difference of square methods on both of these. But in the numerator, what we'll be left with is x plus 2 times x minus 1. And that would get us back to the x squared plus x minus 2. And then this is a difference of squares. X squared is a square and 1 is a square. So this means that we have x plus 1 times x minus 1, that can be broken up into. And notice that whenever we have finished this factoring, this is as much as we can factor it, that we actually do have some cancellation that is occurring right here. X minus 1 and x minus 1 can cancel in the numerator and the denominator, which means that we're not going to treat this x minus 1 as a vertical asymptote. We're going to treat it as a hole in the function rather. And that's what that first blurb was saying for the vertical asymptote case. So this isn't going to be a vertical asymptote, but this one will be over here, right? So if I'm looking at my vertical asymptotes then that would just be where this x plus 1 piece is equal to 0. So x plus 1 could be equal to 0, but that means that x has got to be equal to negative 1. So my only vertical asymptote on this function then would be x is equal to negative 1. So we definitely need to be a little bit careful. We can't immediately grab this denominator and set it equal to 0. We have to make sure everything is as factored reduced as it can be, and any cancellation that can occur does occur first. For the horizontal asymptotes, however, we are in the case where the degree of the numerator is the same as the degree of the denominator, and that just means that we take a ratio of the leading coefficients. So that means our horizontal asymptote is at y is equal to 3 halves, because this is the leading coefficient of the numerator, and that's the leading coefficient of the denominator. And that would be our equations for both our vertical and our horizontal asymptote, okay? Very nice. Let's look really quickly. I'm actually going to give this a pause. My cat's meowing, one sec. All right. Cat dealt with, I'm back. Apologies for that. Let's look at one more example in this section real quick, and then we'll be done for the day. I'll do example 4. I'll bump this up for us right here. Example 4, I'm going to write a little bit from the text, unfortunately. Again, it's a word problem, and I haven't given you all the notes, so I'm going to go ahead and copy it down. It says, a company that manufactures computers has established that a new employee can assemble NT components per day after T days of training. And this function is given by NT is equal to 50T over T plus 4, where T is greater than or equal to 0. So we specifically have this type of rational function modeling the number of components that an employee can produce per day given a certain number of days of training right here, okay? What we want to do is we want to answer two different questions for this. We want to answer what is going on with this graph, first of all, on its domain. Maybe we'll just kind of sketch it between 0 and 100 days of training and see what that looks like. And then we also will just ask what this kind of means in the context of the actual function, okay? So if we want to look at a graph of this, I'm going to go ahead and sketch it off to the right over here. We only need to worry about the right quadrant of this graph. The reason why we only need to worry about the upper right quadrant is because we're dealing with numbers that only make sense in positive terms. T days, if we're thinking about t as the horizontal axis and n of t as the vertical axis, t represents the number of days of training that you have, so it can't be less than 0. And n of t represents the number of components that employee is expected to make per day, which means that it also shouldn't be 0, right? Or below 0, rather, I should say, right? So let's kind of look at what we might expect for something like this then. What I'll do is I'll maybe make tick marks going up to 100, so maybe I'll skip by 10. So I'll do 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then I'm just going to label every 20, 40, 60, 80, 100. And then we don't know exactly what's going on with our vertical axis yet, so we'll wait just a moment to figure that out. We can see that 50t and t plus 4 are both completely factored in both of their terms, which means that we can jump right into looking at vertical asymptotes and horizontal asymptotes. If we were to look at a vertical asymptote for this problem right here, we'd set t plus 4 is equal to 0, and notice that we'd have a vertical asymptote at t is equal to -4. Notice that this vertical asymptote would occur somewhere over here on the left side of the graph. We're not worried about that because that's not even part of this graph's domain, right? T can't be less than 0. It's greater than or equal to 0. We do look like, however, that we have a horizontal asymptote at the line y is equal to 50, right? Because we have a even degree, t to the 1 power, t to the 1 power, and 50 over 1 is just 50. So for our horizontal asymptote, because they're even degrees, we have y is equal to 50 over 1, or just 50. Which means we can and probably should add this to our graph. So maybe what I'll do is I'll again skip by tick marks of 10, so 10, 20, 30, 40, 50. And we'll add this horizontal asymptote at y is equal to 50, or in this case, n of t is equal to 50, onto our graph right here, okay? So there's our horizontal asymptote. I'll remind us what that is right here. Y is equal to 50 is our horizontal asymptote. And then for our actual function, we might include some important points on this graph. Maybe because we're starting at 0, we should plug in 0. If we plug in 0 here, notice that 50 times 0 is 0, and 0 in the numerator means that we're going to have 0 total. So that means that on your 0 days of training that you should be expected to make 0 parts, which seems fair by this company's standards, right? We don't know exactly what it is, but it's fair. Maybe what we should also do is we should sketch a few other curves. Maybe we should try like n of 25 and then n of 100. Maybe those would be good ones to look at. So over here again, I'm going to sketch out a quick table. And we'll do t and n of t to kind of get some input-output values for this function. And just to get us a good idea of what's going on, maybe we'll do, let's just do 20, and maybe let's do 100. I'm going to go ahead and compute these for us directly in the graphing calculator. I'm going to slide this up a little bit so that we see n of t also. There it is right there. To get n of t when t is 20, we do 50. Let me do alpha y equals first. 50 times 20. Maybe I'll do it in parentheses to do it exactly like it shows up. Over 20 plus 4. And whenever we input that, we get this is a fraction. If you want to change it into a decimal, you can press the math button and then go down to decimal and then do that. And you can see that we get about 42. I'm going to go ahead and round it. So I'm going to say this is approximately 42 whenever it's rounded. Okay. I'm going to do the same thing with 100 now. So I'm going to go back over in here, and I'm going to do 100, and I'm going to do 100 times 4 here. And math decimal, looks like we get 12.5 whenever we do that. This shouldn't be right. This looks like I have maybe misinput something right here. 50 times 100 over 100. Oh, I'm doing times 4 and not plus 4. That means I probably messed up the previous one too. Oh, no, I didn't. I just messed it up whenever I was retyping it. Sorry about that. Let me go ahead and retype this as plus 4. There we go. And then we get math frac decimal. There we go. That looks a lot better, about 48. Okay. So then we have these 2 points in addition that we can add to our graph, one at 20, 42 about, so way up here. And then also whenever we get to 100, about 48 right here, okay? So we have these 3 points on our graph then, and we can kind of get an idea of what the behavior is that we see here. It looks like we're really kind of quickly getting up to this point right here, and then we're leveling off and getting closer and closer and closer to that y asymptote right there. But again, because it's an asymptote, we're never quite hitting it, right? And that would be a good sketch for this curve of how many components these employees are expected to make per day after a good number of training days, right? Now notice that just because this kind of output is stalling right here doesn't mean that the employees are necessarily doing a bad job. This right here is just kind of the upper bound on what can reasonably be expected of them, even if they've already been maybe quote unquote fully trained. And we can make a note of that below. Maybe I'll do it in red. Notice that even after, we could say months of training, the expected components produced never goes above 50. And we can say if we want to due to the horizontal asymptote. That's kind of the behavior that's making it behave this way, or that's kind of the thing that's causing this behavior rather. Let me move that up a little bit. So that's about all that I want to talk about for this section then. Again, if y'all have any questions on this while y'all are working through this or any problems in the homework, let me know. If not, y'all have a good day. I'll see y'all hopefully next week.